Everybody. So this morning we have Wolfgang Lueck from the University of Bonn, who is going to speak on the stable Cannon Conjecture.
So first of all, I would like to thank the organizers for the invitation to the conference, for the opportunity to give a talk here. So the topic is the stable Cannon Conjecture, and I will just start with putting this into context concerning three-manifold theory. I will start with the notion of a Poincare duality group, and this talk is about Poincare duality groups in principle. I will start recalling what a Poincare complex is. So a finite n-dimensional Poincare complex is just a finite n-dimensional CW complex, but it comes with the extra Poincare structure, and this is given by a fundamental class in the homology of X with coefficients in the twisted module ZW. So W is something like a first degree Whitney class. Pi 1 acts on Z during this orientation character from the fundamental group to plus minus 1. We have this class, and then you get a Z-pi chain map from the dual chain complex of the universal covering to the chain complex of the covering, and this should be a Z-pi chain homotopy equivalence. You may have seen homology in other disguises saying that certain cohomology groups are isomorphic to homology groups, and all these kind of isomorphisms are implemented by this chain map. So this is in some sense the strongest notion of a Poincare complex, and it gives you all other variants of that. Of course, you are not surprised. You have a closed manifold. It's a Poincare complex with this structure, and the W, which occurred here, is exactly the first degree Whitney class of your manifold. You may have already seen the proof why the manifolds are Poincare complexes. When you have a triangulation of your manifold, maybe after subdivision, there's a notion of a dual cell. So when you have a p-simplex, there's an n-minus pi cell, which is part of a CW structure. And this chain map actually is an isomorphism of the cellular chain complex of this dual structure to the cellular complex coming from the triangulation. And because you have the dual cells, this goes really like this, that you take the dual of the chain complex shifted and it goes here. And since this is even an isomorphism respecting basis, it's actually a simple homotopy equivalence. We will not bother about the difference between simple homotopy equivalence and homotopy equivalence in our talk, because all our groups we will encounter will have vanishing invited groups, and therefore this doesn't play a role at all. So here's a notion of a Poincare duality group, which on a first glance looks much weaker. So you start with the group G, and I would like to have it to be finally presented. Group theorists would like to have only finely generated, because I want to look at fundamental manifolds and they're all finely presented. I will make this assumption from the very beginning. But the main important properties are that the group is of type FP. That means you have a projective finite resolution of the trivial model Z. I don't say anything about its dimension, but the dimension actually is fixed by the last condition, which is a kind of reminiscence of Poincare duality. It tells you that the cohomology of Z with the G coefficients is just concentrated in the top dimension n, that is Z, and 0 otherwise. And there's a rather important theorem of Ball, which is non-trivial, that if you start with a Poincare duality group in this fashion above, it actually comes from a Poincare complex, and the underlying space of the Poincare complex is BG. You need this condition that the projective class group vanishes, but again, don't care. We have not care about it. It will vanish anyway in the class of groups we were looking at. At least I will give an idea how you get from there to there. So suppose BG is a manifold, then this group is the cohomology of the universal cover. By Poincare duality, it should be H0 of the universal cover, but universal cover is contractible. So there's only Z in dimension 0 and nothing otherwise, and by duality you get exactly this formula here above, right? So this is an obvious consequence of this assumption that the group has this property, but the important step is going back from here to here. If you are familiar with group theory, this definition has the advantage. It can be generalized to more kind of stronger version of Poincare duality using dualizing modules, but I will not come into that. So what's the corollary out of the first two slides? Whenever you have a closed aspherical manifold of dimension d, then pi1 of x is one of these Poincare duality groups, because this manifold has a Poincare structure, and we have seen that this implies this weak notion. Of course, one of the big open problems, which was stated by Wall, I come to it later, is the converse. You start just with a Poincare duality group. You see no manifolds occurring. Question is whether it occurs as an aspherical manifold. This was answered very early already in dimension 2. So Beery, Ekman, and Linnell combined their work to show that if you have a two-dimensional Poincare duality group, it is automatically the fundamental group of a closed surface. Good exercise proves the statement that every one-dimensional Poincare group is a manifold group. That's not so hard, but there's a small thing you have to do. So, of course, because I come back to this, I will need the notion of a hyperbolic group very often in this talk. You can use it as a black box, but I would like to give you an idea what's going on here. Otherwise, hyperbolic group means something which we always have at hand. But what a hyperbolic group means. It was an invention of Gromov, which was really a kind of revolution in geometric group theory, and something started geometric group theory. So what is the idea? You have a finely generated group, and now you can choose any symmetric finite set of generators. And then you can look at the Cayley graph. So the Cayley graph of a group is essentially you're taking your group, which is a metric space via the word metric, but whenever you have a generator, you will add an edge to the corresponding group element, so that you see a one-dimensional space. And now you can walk around in this space. That's the reason why you want to look at the Cayley graph. And you can talk about geodesic, you can talk about triangles. And here's the general condition. You would like to have that with the word metric, this space is hyperbolic. So what does it mean? You can start with any geodesic metric space. Geodesic means 2 points can be joined by a geodesic. It doesn't have to be unique though. And the decisive question is whether geodesic triangles are thin in comparison with geodesic triangles in R2. And here's the picture which you probably all have seen. Look at the Poincare disks. That is the hyperbolic space. And you are probably not surprised that the hyperbolic space is an example of an hyperbolic metric space. And if you take any triangle in it, with a geodesic, it looks more or less like this. And this looks thin. Of course, you can also have drawn it a bit thin, but the point is, you will find a point inside its triangle so that this point has finite distance from all of the 3 sides. If you take Rn or R2, this is of course not true anymore. If you give me a number, I will always find the triangle, make it very large, so that there is no point whose distance from all of the sides is bounded, and that means if it were bounded, you see then the triangle has to look like this. It has to be thin. So that's the idea. It's a kind of synthetic metric notion. And the important thing is that this is a property which is a quasi-isometry invariant. I will not bother you with the notion of a quasi-isometry invariant, but this is the starting point with geometric group theory. Roughly speaking, of course, there are many Cayley graphs for the same group. And the Cayley graphs are as metric spaces completely different. But quasi-isometry is just the right notion that the Cayley graph of a group, independent of the set of generators, they are quasi-isometric. That means you have assigned to a group a metric space, or let's say a quasi-isometry class of a metric space. Now you can do geometry on this class, and you get invariance for the group. And the point is, you call the group hyperbolic if it acts, or the Cayley graph has this hyperbolic structure. Quasi-isometry, if you want the definition, write down what bi-Lefschetz is, but now you add an additive constant. And roughly speaking, what happens locally doesn't play a role anymore. A quasi-isometry doesn't have to be continuous, but if you go far away from the distance, they all look like the same. Here's maybe an example. Takes the integers. One Cayley graph is this. There's another Cayley graph, which looks like this, where you attach cells of this shape. They are different, but if you go very far away, they look be the same. That's the idea. Hyperbolic groups have very strong properties. It seems to be a very innocent condition. but those groups are always finally represented automatically, and they have already a finite model for the classifying space of proper actions. If you do not know what this is, read this line. If you have a torsion-free hyperbolic group, it has a finite model for BG. That means the homology is trivial, it's finally generated, it's bounded, concerns the dimension. That's already a strong conclusion from this rather innocent-looking definition. The point, by the way, of Gromov was that he realized that many things you know about surface groups, let's say DN algorithms, and all these things can be transferred to this setting, and hyperbolic groups are common groups. In a sense, you can really make sense out of the statement that a random finally represented group is hyperbolic. I will not do it, but this is not a slogan, you can make it precise. In other words, you choose randomly a finally represented group, it will be hyperbolic. And now comes the main point about hyperbolic groups which we will use. They have a boundary. And this boundary, which is defined in terms of the Cayley graph, let's say, fits everywhere. That's the amazing thing. Namely, suppose you have some geodesic hyperbolic metric space, not necessarily the Cayley graph, on which the group acts properly, co-compactly by isometries. Then you can compactify the space X by adding this delta G to it. And of course, it's not the disjoint union of topological spaces. We have this nice topology on X bar, so that X bar really deserves the name compactification. X bar is compact, it has a metric, and I will not go to what a Z set is, but this boundary is a Z set in X bar. I probably will not say what a Z set is, but think about a manifold boundary in a manifold. That's a Z set. There's a very strong homotopy theoretic condition which more or less survives in this setting as well. And the important point is delta G is independent of X. So I may have completely different spaces, different dimension even, but the delta G fits always at the boundary. This delta G looks in general rather strange. It's usually totally disconnected. For instance, think about a Cantor set, Kapinski carpets or whatsoever. But it can be a manifold in one prominent example. Namely, let's go back to a closed Riemannian manifold of dimension n, whose sectional curvature is negative. Then you look at the fundamental group, and I'm claiming that's a torsion-free hyperbolic group, and its boundary is the sphere, the standard sphere. So what's the point? You're looking at the M twiddle, which has a metric which is negatively curved, and the negatively curved manifold is always the example of an hyperbolic space. Of course, our group G acts on this M twiddle, that's fundamental groups, they always act on the universal cover, probably, actually freely, and co-compactly. And that means that the boundary I have defined in terms of the Cayley graph will fit here, and I'll do the inverse. I will look at the boundary I see for M twiddle, and I know what the boundary was. But now comes this classical result of Hadamard into play. There's a diffeomorphism from M twiddle to Rn, which is essentially given by the exponential map. You take any point in a manifold, takes the tangent space, and takes the exponential map. And this is the homeomorphism. That means when you have a point in your manifold and you shoot out geodesics, yet it's the same as looking in your tangent space, maps going out to infinity rays. But now what's the sphere at infinity? That's the boundary, of course. Right? If you take Rn, the natural compactification is Sn minus 1, because Sn minus 1 gives you always a direction, and this is really what counts. It means the boundary of M twiddle is the sphere, and therefore delta pi is the sphere as well. So now what are the main conjectures we want to address, or which play a role in this context? The first one is by Gromov, motivated to what I mentioned before. He was asking whether when you have a torsion-free hyperbolic group and the boundary is a sphere, then it's always already a manifold type group. The idea is that when people were investigating hyperbolic groups, they very often saw this kind of two disconnected boundaries, strange things. By the way, a good example is takes a free group, takes this infinite antenna you have seen, it goes to infinity, and then you see the Cantor set at infinity. And he was asking, if the boundary is a sphere, does it mean actually becoming from a manifold in general? And this was answered positively by myself and Arthur Bartels and Ferry and Weinberger, at least in dimension 6. I think nowadays we can do also n bigger than 5, but of course 4 and 3 are the usual problems. 2 and 1, I have already given you the answer. So in some sense this question is open in dimension 3 and dimension 4. I will not talk about dimension 4, it's a different story which would go to Friedman's questions about good fundamental groups, but I will not say anything about that. And here is another conjecture by Wall, which is pretty famous, which I mentioned in the very beginning. We know that an aspherical closed manifold has a Poincare duality group as fundamental group. What is about the converse? And it's a difficult question, you see. Remember the definition of a Poincare duality group. If you look at this, where is a manifold? Right? So in some sense, how do you get out of this data a manifold? It's not at all clear. Just this innocent FP condition and the computation of one cohomology group. Therefore, I think this is a pretty amazing conjecture, which you may have your doubts whether it's true or not, but so far there is no counterexample known, and of course it's open. So now what's a Cannon conjecture? Is in some sense you may say is Wall's conjecture in dimension 3, but now for hyperbolic groups. So here's a precise statement. You start with a torsion-free hyperbolic group G. Recall these were groups where the Cayley graph looks like an hyperbolic space. We have a boundary, and the boundary should now be S2. Take a three-dimensional hyperbolic manifold, then its fundamental group is hyperbolic and has S2 as boundary, that I tried to explain using Hadamard. Now the question is just whether this is an equivalent statement, namely Cannon conjectured that if you have such a group, torsion-free hyperbolic, S2 as boundary, it is the fundamental group of a closed and hyperbolic free manifold. And when I say hyperbolic, I mean really sectional curvature -1, the most strongest notion of negative curvature. And this is a pretty amazing conjecture. The interesting thing is that, as you probably know, there were two big conjectures in dimension 3, the Thurston generalization conjecture and the fibrine conjecture. Both have been proven. Last decade by Perelman and 4 years ago by Agel. And then everybody thought, no, that should not be the problem, but it doesn't follow from then. It's still an open question, we don't know what to do. And I know that many people, which are really hardcore three-manifold theorists, are working on this conjecture. And there are it's a certain progress, but to my knowledge, no one really knows how to prove it, although the common belief is that it should be true. This is what I would like to address, and roughly speaking, I would like to prove the Cannon conjecture, but I can't. So let's try to prove it stably, right, as always, right? You have something which is unstable, very hard, do it stably. And that we can actually to the full extent, as you will see later. So let me give you some background about this conjecture. So there are very nice results of Cannon and Cooper, Eskin and Fisher, White and Kapovich-Lieb. If you put them together, you get the following result. If you want to solve this problem, so you start with the Poincare duality of dimension 3, you would like to know where it's the fundamental group of a closed manifold. That is a question which is a quasi-symmetry invariant. It's very strange. I mean, I didn't tell you what quasi-symmetry means, but very different groups can be quasi-isometric. So in some sense, the question whether dimension 3 a group is a Poincare duality group occurring from a manifold is a quasi-symmetry invariant. That, of course, is very nice for the geometric group theorists. Now they can come into business because they can only do things up to quasi-isometry. But I'm not blaming them for it. That was a big thing. If you're a little bit familiar with three-dimensional manifolds, there are these hyperbolic ones and there are the Seifert manifolds. In some sense, more or less, a three-manifold is either a hyperbolic or a Seifert manifold. And I would like to mention what a Seifert manifold is. Usually you have an S1 action which looks like an S1 principal bundle, but you have some extra orbits. But you may say Seifert means you go to find a covering, and then you see a very nice S1 principal bundle over surface. And the S1 going to M bar, because the principal bundle will generate infinite cyclic subgroup of the fundamental group, which is central. And Bowditch could show that if you have a Poincare duality group of dimension 3, which has an infinite normal cyclic subgroup, which of course should come from this inclusion, then it is actually the fundamental group of a closed Seifert manifold. So here we completely solved the problem of wall for Seifert manifolds in dimension 3. The techniques are completely different from the one I will present here. Then Beswinger showed something which is very interesting for us, because he showed, suppose you have a hyperbolic three-dimensional Poincare group, then the boundary is already S2. So more or less the Cannon conjecture is the same as the conjecture of Wall, more or less, because you would like to find a manifold realizing your group as the fundamental group of it. So there's no difference in dimension 3 between Poincare L2 and boundary S2 as long as your group is hyperbolic. Here's another very nice result, which gives you the impression it should be easy to prove the Cannon conjecture. They also showed that if you have an infinite torsion-free hyperbolic group, which is prime, that means it's not a non-trivial way free product, it's not infinite cyclic, and you know it's a fundamental group of some closed free manifold. I don't care how it looks like. Yeah, then M is already hyperbolic, and this group satisfies the Cannon conjecture. So a rather very strict conjecture, because just knowing G is a fundamental group of something implies already that something is hyperbolic, and the Cannon conjecture is true.
Does that use the geometrization?
Pardon?
Does that use Perelman's geometrization?
Yes, yes. Actually, yeah, it's hidden, but most of the theorems I would present at one point use Thurston and use also sometimes Agel, but I will not really say so much about it. So now let's summarize this, and then you think it should be easy to prove the Cannon conjecture. Then we only have to prove the following. I start with some hyperbolic group whose boundary is S2, and it should be quasi-isometric to the fundamental group of some aspherical closed free manifold. And then the rest comes automatic. That sounds very easy, because quasi-isometric you think, come on, it shouldn't be a problem. Of course, it is a problem because you have no candidate for this free manifold, right? And actually, why this is a hard conjecture should be explained by the next slide. Because fundamental groups of closed aspherical manifolds have very nice properties. For instance, they are residually finite and they are Hopfian. If you do not know what it means, nice properties of groups. We know already that all the L2 beta numbers vanishes. We know that efficiency is 0. That means in particular, they have a presentation coming with the same number of generators and relations, what is unusual for a group. Actually, this comes from a Hegard decomposition, if you would like to. And now suppose that the group is hyperbolic, then it becomes dramatic, and now comes Agel into play. Then you know that this group is virtually compact special, whatever that means, but it's linear over Z. So you can embed the group into GL and Z for some big N. So it's a very strong condition on your group. And even going further, you can write some finest index subgroup, of course it means you go secretly to a covering, as an extension of a surface group by Z. And now you see how restrictive it is if the Cannon conjecture is true for a hyperbolic group to be, with boundary S2 to be the fundamental group of a hyperbolic manifold. It has to have all these properties. And now you more or less should get some respect why it's not so easy to prove the Cannon conjecture, despite the trivial looking statement there, which is not trivial. Okay, let me, of course, now you see the difference between 3 and 4. In dimension 4, everything is a fundamental group of a manifold, right? It's different in dimension 3. Okay, maybe I will, if you don't mind, skip this. But this is interesting. Suppose you have a boundary of a hyperbolic group, which looks very strange. And now suppose you have one open subset where it is a manifold. And then it's already Sn. So it's a kind of, some poly calls it a kind of click version. You have something which is bad. It's a manifold at one point, and suddenly click, 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 everything is a manifold. And not even that, it's even a sphere. So kind of rigidity, which is very strange. And of course gives you some hope for the Cannon conjecture in some sense. Okay, this is, I try to get the constants here, and now let me just say the main results. As I said, we are aiming at proving the stable version of it. It means you're allowed to cross with a manifold. But here's our first result, and let's go through it carefully. So you start with a hyperbolic 3-dimensional point-gradient duality group. And our goal is to find a hyperbolic 3 manifold with this as fundamental group. So if you want to find a manifold, of course it cries for surgery theory, right? So what you would like to do is, you would like to construct a surgery problem. So BG is of course the specifying space, and we know that this is a Poincare complex of dimension 3 and finite thanks to Ball, so we can start with our surgery machinery. And the first step will be that we have to have a surgery problem at all. Surgery problem means you have a manifold here with a map of degree 1 covered by bundle data. So as said, BG should be a finite three-dimensional CW complex, so you can do surgery. You have this map, and you can arrange that this map is an homology isomorphism. And now comes the main point. Whenever you have a surgery problem, you have a so-called surgery obstruction, which, because we are in dimension 3, and we want to do surgery up to simple homotype equivalence, it's in this decorated L group, whatever it is, you have an element, whatever it is, and this should vanish. Now suppose for a second we could do surgery in dimension 3, then we would have proved the Cannon conjecture. Because this on the slide would mean that I can change this surgery problem into one where here's a simple homotopy equivalence and we are done. Because remember, we only have to show that BG is the fundamental group of some manifold. We have a homotopy equivalence from M to BG. M has this property, and then the rest is taken care of about the slides I mentioned before. Of course, you can't do surgery in dimension 3. You are probably familiar with that you can't do surgery in dimension 4. The other reason is a Whitney trick. The Whitney trick was you have two disks, let's say 2 disks embedded in your manifold, and you would like to make them disjoint. In dimension 5 and higher, no problem. In dimension 4, you can make them into general position, and you have these intersection points, and now smoothly you have an obstruction. Topologically, you can do it. In dimension 3, the problem is something else. You can make your map 1 connected, and then you want to do the last surgery to make it an homotopy equivalence. But here you destroy the fundamental group, because you are attaching 2 cells, and that kills the fundamental group. Now you have a kind of problem. This is the reason why you can achieve an homology isomorphism. You cannot really control the fundamental group anymore. Therefore, surgery in dimension 3 fails. So that means we are getting close to the stable Cannon conjecture as we can concerning surgery theory. So that's the main point here. So now how do we get something stably? Here's the theorem. We start again with a hyperbolic 3-dimensional Poincare duality group, and it's any smooth. Now you choose a category: smooth, PL, or topological, I don't care. And dimension should be at least 2. Of course, I would like to cross with this n, and then I'm dimension 5 and higher. So let's cross with the BG with n. And now I'm asking the weaker question whether this is a manifold or not. If BG were a manifold, obviously, but now I would like to answer the question just for BG cross n. And what we can do is, we can find a closed, and now depending whether you start smoothly, pale, or topologically, a manifold like this, and we can find a surgery problem with a property that F is actually a simple homotopy equivalence. So crossing with n allows us to get another problem in the dimensions where surgery holds, and then we can solve it, and that is what more or less the stable Cannon conjecture is about. I do not know what I can do with BG, but for BG cross n I can solve the problem. But we can do more, and this is something which I may have not presented in earlier talks, and this is also important. So let's stare at the covering of M corresponding to G. Notice M maps to BG cross N, so the fundamental group is G cross something, project down to G, and take this covering. If N were a point, this would be the universal covering of M. And now assume that N is aspherical, and the dimension of N is at least 3, and then M bar has to be R3 cross this manifold, and even better, you can compactify it to a compact space whose interior was of course M bar, and now we have a homeomorphism of pairs of this compactification, the boundary of this, and now you get D3 cross n cross S2 cross n. Why I do expect this to be true is the following. Suppose I have a hyperbolic 3 manifold. Then we know its universal cover was R3. We know we could compactify it to a disk. So if n were a point, then I have just said that the universal cover of an hyperbolic 3 manifold looks like D3 cross S2 after compactification, and we can arrange this compactification. This is not only because we want to have a much stronger statement than we did before, but in some sense we need this statement for the proof, as I will try to explain later. So these are the theorems. Roughly speaking, this says when you start with an hyperbolic three-dimensional Poincare radio group with the right boundary, we have a surgery problem with trivial surgery obstruction. Problem, you can't do the surgery. If you stabilize, the surgery obstruction is still 0. You can do surgery, you get a stable answer, but we can do more because we have an idea about what the universal cover of M is. It allows a nice compactification, which is homeomorphic to something of this shape. So as I try to explain, the Cannon conjecture does imply the two theorems. So if somebody will prove the Cannon conjecture, our paper is completely void. But so far, not the case, and we hope that our paper will be accepted before somebody proves the Cannon conjecture. By the product formula, it's clear why the first theorem applies to the second one. There's a formula when you cross with n, gives you the surgery obstruction of the product in terms of the surgery obstruction before, and if it was 0, you get 0. That means that this slide here is implied by that slide. This is a different story here. And now let's try to understand how we could, in principle, come back. Now notice I have this manifold M, which comes from the last theorem. So M was mimicking BG cross N, and it turns out by the Farrell conjecture, M is a homeomorph, is unique up to homeomorphism. So we have assigned to our group G in any manifold N, an invariant, a manifold.
Are you assuming N is aspherical here?
N is aspherical, yeah. If you look at, it should latest appear here, otherwise I have, yeah, right. And also what I'm saying here is that I'm assuming aspherical. And now suppose you take the N to be the torus, which is in the most natural case. So you look at BG cross a torus, and now you would like to get from our result to the Cannon conjecture, and this only is a mild problem you have to solve. M must be homeomorphic to M prime cross TK for some 3 manifold. This is utterly, let's say, tempting, because now you may have a candidate for M prime if you would understand M. But of course, as I said, the Farrell conjecture is something which spits out by surgery. You don't have the hand on your M. But in principle, the Cannon conjecture is equivalent to the question whether for what I did before, M prime cross TK exists, which is just giving the M back. But as I said, I'm not claiming I can prove the Cannon conjecture. So I want to do surgery theory, so I should better have one normal map at all. This is usually a problem. You start with a Poincare complex, and if it should be a manifold up to homotopy, its p-bag normal fibration should have a so-called vector bundle reduction. Because a manifold always has a normal vector bundle, and this p-bag normal fibration mimics the vector bundle. So there is an obstruction for a Poincare complex to be a manifold, namely you have to find a vector bundle reduction, or in other words, you have to find at least one normal map. Right? So for X, you have to find a manifold with a map of degree 1 covered by this bundle data. And I think every talk should have at least one complete proof, and I will try to prove this because it's easy. So how do you prove that? That you have this if you start with any Poincare complex. So you have to check that stable vector bundles over X in this situation are just classified by the first and second Stiefel-Whitney class exercise, algebraic topology 1. Then you can choose a k-dimensional vector bundle over X. This will be our candidate. With first Stiefel-Whitney class of psi is X. The second one is just the cup product of the first. Now you have to apply a spectral sequence argument. It's now not really oriented Bordism, it's twisted Bordism, which ensures that you have a map from M to X, so that M has this as Stiefel-Whitney class, and this map has degree 1. If W1 of X would be trivial, this has to do with omega 3 of X, and there's this statement that the map from omega 3 sending a manifold to its fundamental class is just surjective. And you do the twisted version of this. So what you have constructed now is this. Easy. And now the rest is also easy, because we have arranged that the first Stiefel-Whitney class of the pullback of the bundle is the Stiefel-Whitney class of M. Now you apply the Wu formula. It tells you that the second second Stiefel-Whitney class of M is this, but this is the second Stiefel-Whitney class of the pullback. So the M has the same Stiefel-Whitney classes as F star of Xi. So you may stabilize and you get the bundle maps. That's all. Okay, now comes more machinery. So now I have to go to this kind of defining the surgery obstruction. And this is now based off, let's say, the theory of total surgery obstructions. But we will do here a very elementary and also in some sense a little bit extraordinary case, because we can assume that the so-called Farrell-Jones conjecture is satisfied. Take it as a black box. It satisfies for all hyperbolic groups. And we also know that we have one normal map. And now I can give you a much easier definition of the total surgery obstruction than the one you would find, for instance, in Andrew Vanitsky's book. But you need some ingredients. So as I said, we have found already normal map of degree 1, and we would like to find something with vanishing surgery obstruction. And we will see the total surgery obstruction is just the only obstruction you will have to solve this task. Of course, you may change your normal map. I have given you one. It may be the wrong one. So I have to pick the right one now. And now recall that this is a set of all normal maps. These are these diagrams. It has a map to the L theory of the G. It's a simple version just given by the so-called surgery obstruction. And the surgery obstruction is 0 exactly if you can do surgery. Right. And now I fix one of the normal maps I found, called it F0 bar, it's a kind of base point. And now the main technical ingredients is this kind of diagram, which you can find in Andrew's book, or you can find it very nicely explained in a paper by Tibor Mako, Philipp Kühl, and Adam Mole, that you have the following diagram. You start with a normal map, and now you don't take the surgery obstruction of it, you subtract the surgery obstruction of this base point. Sorry. Here is the standard identification of n of x with this homology group after you have chosen one of these base points. And here you see the L-series spectrum, the periodic one, but I truncate at 1. So the homotopy groups of this spectrum are 0 in dimension 0 and lower, and they agree with the L-series homotopy groups here in dimension 1 and higher. And there's always a map from this connective cover to here, which gives you a map downstairs. And here comes the black box, namely the Farrell-Jones conjecture, which tells you you have an assembly map here, which is an iso. So you have identified this map here in terms of surgery obstruction with this map here, with more or less a change of theory from the connective L-theory spectrum to the periodic one. Now again, an easy spectral sequence argument shows that this map is injective, and if you want to discover whether an element comes from here, you have to apply a certain edge homomorphism to it, which goes to L0 of 0. It's really elementary. If you think about it, you have connective K theory, L theory, just the sequence collapses to more or less to this exact sequence. So now we look at the following composite. You take n of x, you take the surgery obstruction, you go back with the assembly map, and you apply this map here. So I'm taking this diagram, forget this part, I run around like this, and then comes the map here. And now if you just make an elementary diagram chase, you will see that there is one element, S of x in L0 of z. So that for every element in n of x, this map mu sends this to S of x. It's an elementary chase. You can sit down, you will figure it out in 1 minute. I think I will not talk about this. So you have an element in Z, which is the obstruction to finding some element here with surgery obstruction is 0. As I said, you have started maybe with the wrong one, but you know how now to change it to get the right one. So here are the main properties, as I said before. This is maybe the main upshot here of this discussion. You have a normal map with target x. This is an assumption. And you would like to know whether the simple surgery obstruction vanishes. You can arrange this by changing a normal map, by just looking at the total surgery obstruction should be 0 in Z. So you have an integer obstruction which decides the question whether your surgery problem has a solution or not. And this obstruction is actually a homotopy invariant of x and depends hence only on G in our situation. The reason is, for the experts, I can express the total surgery obstruction in terms of symmetric signatures of your manifolds in the sense of Kranitsky's, and they are designed to be homotopy invariants. Okay, now comes the next ingredient which you wouldn't expect here, and which are the reason because I have 2 co-authors, because they are really have developed this theory of A and R homology manifolds. I must admit this is something I do not like, this notion, but if you want to do something about manifolds, you very often have to go through them. It's very strange. So they are ugly. Steve and Small are not here. Very good. So what is it?
Dry tape, you know.
Yeah. It's too late. So an A and R homology manifold is in A and R, an absolute neighborhood retract. I never can recall the definition. But something you embed it somewhere and then you can collapse it. But now comes things I know. It has a countable basis for the topology. Its topology dimension is finite. That is important. The covering dimension is finite. It's locally compact. And now comes the reason why we call it an homology manifold. The local homology, so the stalk of the orientation sheaf at a point x is what you would expect from a manifold. Right, by excision, this is the homology of a disk, a sphere, and this is as you see there. Actually, there was something like this on the blackboard when I defined Poincare duality groups. Remember? There was also some group which was just in 1 dimension, a Z, namely in the top dimension, and 0 otherwise. So if this is compact, you will call it an A and R homology manifold. You can also have a notion where you have a boundary. I will use it, but I will not go to the definition. Of course, every closed manifold is such of these guys. And if you go through these things, this is either part of the definition of a manifold or it's obviously true. And this is the fact that a manifold is an A and R because you can embed it into a Rn. That's the reason. But also there are many manifolds which are not there are many A and R homology manifolds which are not a manifold. Here's a very good example. Take an homology sphere. Homology, not homotopy sphere. And suspend it. It looks like a manifold on the first glance, except for a set of measure 0. And you should not discard it. It's the cone points where you suspend. If you look at the length there should be a sphere if we were a manifold, but it's only this homology sphere. And we have homology spheres which are not homotopy equivalent to spheres. So for instance, if you start with the Poincare sphere in dimension 3, you will get an example of a 4-dimensional A and R homology manifold by suspending it. And now guess what happens if you suspend it again? It becomes a manifold. That's a big theorem of Edwards. So you see that this is all very strange territory here. So now, of course, I like manifolds. So what is the obstruction from an A and R homology manifold to get a manifold? And this was figured out by Quinn. By the way, it's a very interesting story. Quinn made a mistake which Capel told him, and the result was a nice Quinn obstruction, because this resolves the mistake he was doing. So mistakes can be very productive. So what he did is, he proved there's an invariant taking value in 1 plus 8z, so it could be 1, 9, minus 7. It has the following properties. And the first one is already the amazing one. You take any open subset, you can take its obstruction, and it's the same of M. So So it's a local invariant, and I mean very local, right? You have to compute only at one point. It's multiplicative, and here comes what we want. If M is an homology manifold of dimension 5, then M is a topological manifold exactly if this obstruction vanishes. And there's a nice relation between the Quinn obstruction and the total surgery obstruction, namely they are related by this formula, at least if you start with an spherical closed an homology manifold of high dimension. So just to summarize, we have Quinn's obstruction, which is defined if you have an ANR homology manifold that you need. Recall that the total surgery obstruction didn't need an ANR homology manifold, just need a Poincare duality group. But if you go to the situation of an spherical manifold of high dimension, they coincide. And now I can use the property of this one and that one, combine them in my situation, and I will get the result. One thing I would like to point out that you get an idea. Suppose I have a very large manifold. It goes from the Newton Institute to Bonn in a homology manifold. And somebody at the Newton Institute looks at it and say, hey, it's a manifold point. Then it's also a manifold in Bonn, right? This is pretty amazing if you think about it. Of course, yeah?
How does this work in the example of a suspension of a multisphere?
It doesn't work because I didn't tell you about the distro and disk properties, and this is not missing. Sorry, I was cheating. Coming back to this, of course, what should be behind of this is that all in a homology manifolds are homogeneous, right? A manifold is homogeneous. You take 2 points, and there is a homeomorphism, sending one point to the other. It's one of the big open conjectures in R theory, and you will see whether there will be a proof coming up soon by a certain expert on this field, not by me. That would be very important because then you could really go on with this stuff. So now let's try to prove what we wanted to prove. We have nearly everything together. Remember, we want to show for an spherical finite three-dimensional Poincare complex that its total surgery obstruction vanishes. And X was BG, G hyperbolic group, Poincare duality. So the surgery obstruction also satisfies the product formula. And I only need to show that this vanishes. Remember, that was the deal about the total surgery obstruction. But now, by this product formula, and the torus is a manifold, its obstruction is 0, I only have to compute X cross T cube. So now I'm in business. Instead of working in dimension 3, I have made my setup so that I can cross with the torus, and now I'm in the high dimensional situation. So I only have to show why this is true. And now I'm using all the machinery of ANR multi-manifolds. And why is this really, and I have to admit, a very nice machinery? You remember that I went to the one connective cover of the L series spectrum. It was due to the fact that the map from the normal map to the L group is more or less the corresponding map from the connective cover. But if you allow ANR homology manifolds, you can put in the periodic L series spectrum. In the search exact sequence, the map from the normal invariance to the search obstruction is the Farrell-Jones assembly map. And you can do all things you like to do, but you don't have to do one connective cover. When Gromov actually saw this theory, called it the theory of lost tribes, because it's very strange that you have to go to the one connected cover. The reason is that the manifold has zeros Pointrying class 1. And in some sense, in our multi-manifolds can have zeros Pointrying class the Quinn obstruction. That's the idea. And that you can now allow variance of the Pointrying class. The zeros one means simply you can also capture something in pi naught of the LCO spectrum. So now comes in some sense the hard part, which I will, I think I will probably skip it. So there is now we come with compactification. Actually in this paper are also hidden some techniques which are interesting for people who want to compactify spaces. It's hidden, but it's very nice. Recall that we have a compactification of X by adding a boundary. The boundary fits everywhere. That was the point. But now you have this homotopy equivalence. And now we have found a way of pulling back a boundary here to the boundary there. Of course, in an intelligent way, so that all the nice properties you have survive. It's really a compactification. And the main point will be that this is a Z set, what you add there. I will go through the details, but that you need. And now comes, in some sense, the dirty trick which took me at least 3 months because I was not aware of A&R multi-manifolds. So as you know, if you have a manifold, it has a collar inside, right? You can just, and now try to find a collar inside an A&R multi-manifold. Good luck, I couldn't find it. And I remember I got really sometimes angry about it because I'm not used to get stuck with one problem for 3 months. That gets on my nerves. So I added a collar to it. And then I realized, hey, it's also an A&R multi-manifold. It doesn't matter how you glue. So you can just add a collar. You get a bigger A&R multi-manifold, which contains this. And now it has a manifold point because our boundary was a sphere. I've added a collar, and inside the added stuff, there's a manifold point. So I have this compactification, which is now very important, you see, because I can enlarge it even to y. M twiddle sits in y, but there's also a u in y, which is homeomorphic to R6. So M twiddle is in y, u or R6 is in y. Now you can do what imagine what I'm doing. I'm taking the obstruction I want to compute, x cross t cubed plus 1. This is the same as the things I started with, because I'm crossing with t cubed. But this is the Quinn obstruction. So to define this here, I only had to use the total surgery obstruction. Quinn wouldn't apply because I have no A&R multi-manifold around. If in dimension 3 I would have an A&R multi-manifold, I would know precisely it's a manifold and I would be done. But now I'm in the Quinn realm, let's say, and of course the covering M twiddle to M is a local homeomorphism, so the obstructions are the same. I go to this larger manifold. This has a manifold point. This is 1. And since this equation is true, some number theory tells you that this is 0, and therefore you are done. So this, sometimes the trick we have played here is, you have a very bad sink, but it has a very nice collar, which I added. Here it was nice, that is bad, but because it was nice here, it's also nice inside. That was the trick. It's very strange in some sense. Okay. Let me say, I will not talk about it. I told you we are able to pull back boundaries. This is a very nice technique, and for someone who wants to compactify things, I think he can address me in private, because I think we should have a break anyway between 2 talks, so I would stop here.
Are there any questions or comments?
So how do you know that the boundary is smooth? Because otherwise not smooth, but
Not smooth.
the manifold.
Yeah, you
otherwise
see,
you
the dirty trick is, I take this M bar hat, I take this union, this is my Y. Just I take the boundary,
But you do know the boundary.
cross it, and add it to it.
So you do know the boundary.
Yes, but of course I can attach it. Usually if you have a manifold and you want to attach something to it, it's not so clear to say the manifold, but for A&R it's computation. I want to point out, I didn't explain what a Z-set is, but if you encounter these things, it's a very important notion. And example is the boundary of a manifold in a manifold is a Z-set. Just for if you are interested. Z-set is important.
Just if I understood, coming back to the Cannon conjecture, you said if you took your group G, you needed to show it was quasi-isometric to the fundamental group of some 3 manifolds.
Yeah.
But now you have this degree 1 normal map with all the good properties, so that's a 3 manifold. So is there?
Yeah, the problem is I only know that it's homology isomorphism, but I do not know whether pi 1 of m is quasi-isometric to. Actually, it could be that it's true, but I can't prove it. That's the problem. It's a good point how you could try to solve it, right? That you now know enough surgery that you get some quasi-symmetry isomorphic group, but we only can test the homology. Is all we can, even with all coefficients, as you know, but we are not able to figure that out. I should say that the people in dimension 3 trying to investigate the boundary. If the boundary has a certain Möbius structure, and then you get the Cannon conjecture, but they can't do it. So they are taking this problem with a completely different point of view.
Is it possible to explain an example of a A-nar manifold which is not a manifold, or maybe give some hints about how one?
Yeah, I try to give this example of suspended Poincare disk.
No, I mean one with non-trivial Quinn obstruction.
Oh, this is a very deep construction. You see, in the beginning, Quinn had the obstruction. No one did know whether it may be over zero. People hope for that. Actually, I also hope for this because actually here's a conjecture I have. Any aspherical manifold has trivial Quinn obstruction. The point is the constructions of manifolds with non-trivial Quinn obstruction is very hard. It's using controlled surgery, and they never will give you aspherical examples. And one does know that if the Novikov conjecture holds, the Quinn obstruction is a homotopy invariant. So if it is non-zero, you have now a strange thing you assign to a Poincare group as an integer, which is an invariant of the group, which should be the Quinn obstruction, but it should be zero in some sense. So my conjecture is aspherical manifolds have trivial Quinn obstructions, and if you ask Steve and Shmuel, they don't believe that. And I must admit, probably no side has really an anchor what to do, right? So it's wishful thinking. And I'm an optimistic guy, and that's true.
There's no more questions, I thank Wolfgang again.
Thank you.